Hey everybody, we are going to go over vision today. Going to go over the eyes. This is one of the first senses we're going to hit. As you are doing this, please make sure you are filling out the watch guides as we roll through. This is going to be called Vision A, and then either tomorrow night or over the weekend, I'm going to have you watch Vision B and fill out the watch guide. So anyways, as we roll through, the first couple things we want to talk about is the idea of transduction. This is, and really transduction doesn't just happen in vision, it happens with all of our senses. That is, and we've talked about it before, we just have not used this term. But this is the transformation from the stimulus energy into the neural impulses. So this is where it essentially goes from the sensory neurons to the neurons that then get passed on up to the brain. All right, so this is kind of goes. We have special neurons that sense whatever they're supposed to sense. Well, your sensing neurons are not very big. So remember we talked about interneurons. They're the ones that kind of talk between the sensing neurons and motor neurons and all that. Well, that term is actually called transduction. Now, when it deals with vision, phototransduction gets a little more in depth. That is the conversion of light energy into neural impulses that the brain can understand. You know, if we were able to open my head up and shine a light literally on my brain, it's not going to sense. I'm not going to sense light. All right. So light comes from the photoreceptors in our eyes, and the act of taking that physical attribution of light and turning it into something that our brains can understand, that is the term phototransduction. So same thing with sound, the fact you're hearing my voice. You know, if we opened up our head again and just had vibrations of my voice, if that was the case, then our brain could actually just sense those vibrations, then nobody would be deaf. Deafness or hard of hearing literally comes from the inability to take that physical vibrations and interpret that. And that's what transduction does when we get into the audio part. But anyways, phototransduction is the literally changing or converting the physical, we're talking about physics, the physical properties of light and turning them into impulses that our brains can understand. And then once our brains can read those, then we can interpret that. I've talked about light energy, and that's essentially all what we see. Our eyes are transducing light energy into things that we can and understand. The human eye is fairly limited on the energy spectrum on what it can actually see. As you can see in this right here, let me go to my laser pointer. This right here, this is the wavelength spectrum going from gamma rays all the way to broadcast bands and all that. Very limited spectrum. All right, and of course you've all been through art growing up. You know that white light is made up of, the rainbow. You've always heard Roy G. Biv, all that. So I'm not going to get into that much, but the stimulus input that our eyes see or that our eyes pick up on is light energy. Light has three characteristics. All right. Wavelength. Remember, these are waves. You know, the larger the waves, change on the amount of energy. So you're looking at wavelength, which gives you your hue and color. So from one wave to the next wave. All right, that is your wavelength. Your intensity is brightness. That's how often. And then saturation, how much it is. That's purity. So wavelength gives you hue and color, intensity gives you brightness, and saturation gives you purity. Wavelengths, as I mentioned, from the top of one wave to the top to the next wave, gives you the dimension of color. The shorter your wavelengths, you're going to be blue. Now, if you're talking about this probably makes more sense when we're talking about sound, because your shorter wavelengths, your faster wavelengths are going to be higher pitched, whereas your lower wavelengths are going to be lower pitched. When we're talking about light, when we're talking about hue, then you're talking about color. So you're talking about your reds. The red side of the spectrum is very long waves. The blue side of the spectrum is very short waves with high frequency. All right. So that's your hue. Your wavelength is the distance from the peak of one to the peak to the next. So that gives you your wavelength. Your hue, again, is dependent on the wavelength colors. So your violets, your indigo, your blue, those are much longer wavelengths. Your reds are going to be much shorter wavelengths. Okay, and 400 nanometers to 700 nanometers are the different wavelengths. And we can actually see a bit beyond that because we can see millions of colors. But those millions of colors are going to fall within that wavelength of the larger spectrum. And we're going to talk about that in a little bit. Your intensity is, if you're looking at your wave, how large your wave is this way. All right, so you've got higher the amplitude, going to be more intense that your color is. So if you're looking at blues, this is a very intense blue. With your small amplitude, it's going to be dull colors. It's going to be soft sounds. Large amplitude, loud sounds, bright colors. Small amplitude, dull colors, soft sounds. You think of this really gets into how much energy is within the wave. And here's an example of the color blue with varying levels of intensity. As intensity increases or decreases, the blue color looks more washed out or darkened. Never mind. Purity deals with saturation. This is the most saturated. This is the least saturated. You can almost not really tell a difference between these two. You can't hear. And that brings us to the eye. All right, you will need to know the parts of the eye and what they do and how they allow you to see. All right, and actually you will need to know the order of which light passes in order for us to see and how we see. So we're going to get into this a little bit. All right, the first thing I want to mention is the cornea. That is the outer part of the eye. The next moving inward is the iris, which is the opening of the eye. The iris, which is the muscle around your pupil. Your iris it's actually a muscle. I don't know if you all knew this, but your iris, the colored part of your eyeball, is a muscle, and it expands and contracts just like your bicep or any other muscle. And it can be torn like any other muscle. I'll show you a picture, I think, a little later of a torn iris. It's kind of gross. But as light, if your light, here's your candle. Light passes through the cornea and then into kind of past the iris and then into the pupil. And the pupil is, of course, the opening. All right, that gets bigger or smaller to let more light in or less light in. It then passes through the lens. I'm sure you all know this, but your lens actually flips the image. So what we're actually seeing, if it was raw information, if our brain didn't fix it, everything we would see would be upside down. And that's kind of right here. Your retina, the light will then pass into the retina. And the retina is actually where all of your visual stimulation, your vision sensors are. It's actually on the back of the eyeball, which makes sense. That's where everything goes. So in the back of your eyeball, you have a series of rods and cones, and we'll get into those here in a little bit. But rods and cones are the things that sense light. Cones sense color, but are only used in highlight situations. Cones don't see color, but they fire in low light scenarios. That's why when we're in the dark, a lot of times everything we see seems black and white. Now our brain sort of covers that up by thinking, well, it's just dark. But if you're looking at the pure raw data that your eyes are sending, there is no color when it's very, very dimly lit. The next part is the fovea. The fovea is an area in the back of the eyeball that has a high concentration of rods and cones. And this is the area of the eye where your vision is the most clear. Remember yesterday or the other day I talked about your clearest point of view is actually only about, if you stick your thumb out, about the size of your thumb. All right, and the reason is of your entire visual field, whatever gets reflected on that part of the back of your eye is where that's the most amount of rods and cones. And then below that, just below the fovea, is where your optic nerve goes into the visual cortex. Remember it goes from your brain and moves all the way to the back of the visual cortex, which is in your occipital lobe. All right. That is also where your blind spot is. And we're going to spend some time, hopefully, whenever I get back, I'm going to show you actually where your blind spot is. You're going to see it. Your brain does a good job of covering it up. But the reason why that's a blind spot is because since that's where your optic nerve leaves, there are nerves there. There's no photoreceptors there. So there's nothing there to sense the light that's being reflected back here. So it'll freak you out when we find it. All right, but everybody has a blind spot. We could do it like this. You can try it. I tried. It's harder on a computer than it is actually with a piece of paper in your hand. You can find it if you go to YouTube, type in blind spot test. The very first option that comes up will show you how to do that. You can spend some time now if you want to, but I've tested it, and it's a lot harder to find your blind spot looking at a computer screen as opposed to actually with a piece of paper in your hand. So when I get back, we can talk about how to do this. So again, the cornea, this is a transparent tissue where light enters. That's the outer part of the eye. This is kind of a review. The iris is the muscle that expands and contracts to change the size of the opening, which is the pupil. The lens focuses the light on the back of the eye, the retina, and of course the retina contains sensory receptors that process visual information and sends it to the brain. The lens is transparent. It's a transparent structure behind the pupil that changes shape to focus images on the retina. And by that I mean, if you are looking at something close, all right, your lens is actually going to change shape to see this thing very close as opposed to looking across the room. All right, if you go like this and then lift your eye up, everything looks almost cross, like you've got a cross-eyed. All right, but if you focus on what's at the back of the room, then that becomes in focus. And if I put my finger up here, it looks cross-eyed. It looks like I've got two. All right, that is your lens changing shape to focus on what you're looking at on the back part of your eye. The accommodation is the process by which the eye's lens changes shape to help focus on near or far objects. But remember, the idea of the lens's job is to get things focused on the back of the eyeball, the retina, which is where all your photoreceptors are. And so, I had some people ask about, being nearsighted or farsighted or not having to use glasses. In those scenarios, essentially what happens is the shape of your eyeball does not match the shape of what your lens thinks it needs to be. So in nearsightedness, this is a condition in which nearby objects are seen more clearly than distant objects. What's happening is if you look here, all right, it is the most focused part of the reflection is actually not on the retina. It's in front of the retina. So the stuff that you can see far away is actually focused on the retina here. Farsightedness, a condition in which faraway objects are seen more clearly than near objects. Actually, I may have gotten that one wrong up here. Farsightedness means that the reflection, the best part of the most focused part of the reflection actually happens behind the eyeball. So the near objects are seen as fuzzy. Here, the farther objects are seen as fuzzy because it's in front of the retina. And in farsightedness, the far away subjects, the near subjects are focused behind it, behind the eyeball. And I'll get a little more clear on this a little later. So again, here's another example of how eye shape affects. In nearsightedness, you see stuff clearly here, all right, but the focus falls in the front of the retina, and on farsightedness, the focus falls behind the retina, so it's just not as clear. And this is where we're going to stop. We'll pick up with this part on Vision B. Hope you all are having a good day, and don't forget to do the watch guides. I'll catch you later. Peace out.